Good evening, everyone.
Good evening.
This is Agripakwisuka. So we'll be doing a stream on power system for this evening, and then we'll do control. For control systems, we'll do the stream tomorrow in the afternoon around 3 day, because control systems is Monday at 3 p.m. So tomorrow we'll do the stream in the afternoon, and maybe Monday we'll do another stream before the paper so that we'll complete everything. Okay, so we'll be doing power systems this evening. All right. So the previous video, Tamakloe took us through unit 2 up to symmetrical components, and then he left the unsymmetrical faults out. So we'll just briefly go through unsymmetrical faults. I'll give a general overview of everything, and then since you already know symmetrical components, it's very easy to understand. So we'll do unsymmetrical faults, and then we'll continue the unit 3. And for unit 4, we'll do it in the first stream, probably Monday evening. And then if you're unable to finish, we'll continue Tuesday morning, because PSA is also in the afternoon. Yeah. Okay, so let's start. Alright, so before I start everything, we already know that. So let's do some recap. We know that V phase. We know that V phase is equal to okay. Okay, so we know that V, let me call it ABC, is equal to ZABC I, let's say ABC. You already know this. So let's say, let me just do V phase, Z phase, I phase. Okay. So from here we know that we know if we want to convert from the phase voltages to symmetrical components, let's say V phase will be given as A times symmetrical component. The same way I phase is A IS. So from here we got AVS equals Z phase AIS. People are wondering why the Z comes before the I. It's because Z is a 3 by 3 matrix. ZAA. So Z is a 3 by 3, and then I is a 3 by 1. Alright, and I is a 3 by 1. So if we want to do a matrix multiplication, we can't do IZ because I is a 3 by 1. So we can't do 3 by 1 by 3 by 3. That's why we write ZI. That's why it's Z times I. Okay. So from here, if we continue, we have VS given as A inverse Z phase AIS. And if we do VS over IS, we have AZA. So we are still doing a recap. Very short recap. So if we take a 3-phase system like this, let me stick. And this is a ground impedance. This we are taking a balanced load. If we take this load, let me call here phase A, phase C, and phase B. So this is to ground. So if we have this balance, when we do this matrix multiplication, we are expecting to get 3Zn plus Zy 0 0 0 Cy 0. Okay, this is information that we already know. After doing the matrix multiplication, you're supposed to get this. Okay, so just a fact that you should know: if you have ZAA, CAB, So this is, let's say, generalized impedance expression or matrix expression. If we have this, and then there's a balanced load. If the load is balanced, you realize that you get an expression like zy plus. So if you are using this balance, okay. So you get expression zy plus zn, zy, zy plus zn, zy, zy. See, can you, can you, okay. Zy plus zn. So this will be a expression for z phase. Now you get this by, solving this guy, which is in the slide, so you can just check. So from here, what you realize is that if you have a balanced load, let's say they give you the question, let's say in this form, they tell you that it's a balanced load. Like, what can you infer from here? You should know that if it's a balanced load, then ZAA, ZAB, and ZCC should be equal. So you should know that ZAA should be equal to ZBB, should be equal to ZCC. Also, so we say that the diagonal components should be equal and the non-diagonal components should also be equal, because you can see zy in the others. Also, if it's a balanced load, this is your zs. If it's a balanced load, your zs, that is that the non-diagonal components are all 0, and then you only have values for the diagonal components. Alright, so this is all for recap. So let's move on to unsymmetrical faults. Okay. Alright. So we'll start with single line to ground. Single line to ground fault. Okay. Okay, we are starting with single line to ground fault. Okay, so let's say we have, from, we can take these are our 3 lines. Okay, let me read what the diagram. Okay, so we have our lines like this. So if we have a line to ground fault, then let's see on phase, let's say phase A, we have a line to ground fault here. So the fault is, how do you even draw this diagram? Hey, it's not like that, but let's take it like that. So let's say this is our fault. Our fault is on phase A, this phase B, and this phase C. That means there's a phase A fault current. There's no phase B fault current because the fault didn't occur at phase B. There's no phase C fault current. So if I want the symmetrical components for this fault current, I'll do I0, I1, I2. This matrix should be equal to A inverse IA, IB, IC. Please, one more thing you should know. You know our A inverse is 1/3 of 1 H squared, 1 H squared H. And then our actual A is 1 H squared H, 1 H squared. So if you look at these two, realize that okay, so if you try to get a relationship between the A and this component here, you realize that this is a conjugate of this, because if H is equal to 1 angle 120, if we want to do H conjugate, you know 1 angle 120 can be written as cos 120 plus J sine 120. If we want to do a conjugate, just because 120 minus J sine 120, which is cos, cos of negative is the same as positive, so you can write cos negative 120 plus J sine negative 120. So you can see that the conjugate of H, so H conjugate is 1 angle negative 120, which is the same as 1 angle 240, which is the same as H squared. So if you look at this and this, you see that where A was H squared, this is H. Where A was H, that's H squared. So you realize that this is conjugate of H. That means that A inverse is the same as 1/3 A conjugate. This is something you should know. Just keep it somewhere. You might need it, you might not need it. Okay, so let's move on. So now there's a force at A. So the force current is in A. So A has the current is flowing in A, or the force at A. There's no force current here, there's no force current here. So if you write our symmetrical components out, we're given as A inverse is 1/3 1 H squared 1 H squared H of IA is IA, IB 0, IC 0. So if we try to write an expression for all the components, please let me clean some parts. Okay. So if we are doing unsymmetrical faults, by the way, those who might have just joined us, single line to ground fault. So we write an expression for I naught, giving us 1/3 of IA. That's all, the rest is 0, 0, so we don't have anything. We want I1, giving us 1/3 of 1 plus h squared ia. If we want I2, we're giving us 1/3 of 1 plus h squared plus h ia. And please, this is an expression you should know gives you 0. That means I1 gives 0, I2 gives 0. That means that when there is a single line to ground fault, all you need is I0. When you get I0, just multiply I0 by 3 and you get your IA. That's it. So that's when the fault is at A. That means that if the fault was at B, that means it would have been 3I1 equals IB. Similarly, the fault was at C would have been 3I2 equals IC. The four kind. Yeah, these are the expressions you need. Okay. And then you should know that whenever there's a fault, generally we take a fault impedance, ZF. So let's say the fault occurred at this point. There's an IA that's going to 0. Sorry, that's going to ground. But we'll put a fault impedance there, ZF, before we get to ground. Usually this fault impedance is 0. But in case they give you a value, just in case they give you a value, that's why we are including it here. And then you should know that if you have, like the balance load we had, let me redraw the balance load. So this is our impedance to ground, ZF. You know that if the load is balanced, we have, let's say, IA, IB, IC. So assuming this impedance here is the same as this impedance here and is the same as this impedance here, that means that the current coming here, IN, will be equal to IA plus IB plus IC. If we assume balanced impedance, then the currents are the same. So we have 3IA. Okay. Now, the current that we represent in the circuit is just IA. We don't want to write 3IA. So, to reflect that, you see, if we want the voltage drop here, it is, let's say, V fault will be ZFIN. But IN is 3IA, so that will give us 3ZFIA. The current that we'll be writing is just IA. That means if we want 3 times the current to pass through ZF, then we represent ZF as 3 times ZF. So wherever you see, that's why wherever you see an impedance to ground, we write 3 times that impedance. Okay. All right. All right. Sorry, everyone. Network was. Okay, so let's continue. All right. So from symmetrical faults, I'm making reference. From symmetrical faults, realize that our ZS was, I'll mention it again, 3ZN plus ZY, 0, 0, 0, ZY, 0, 0, ZY. Okay, so if we do any, if we want, let's say, voltage, the voltages, symmetrical component voltages, we're giving us 3ZN plus ZY, 0, 0, 0, ZY, 0, 0, 0, ZY, multiplying I0, I1, I2. So from here, realize that if we want V naught, it will just be 3ZN plus ZY, I naught. If we want V1, it will just be ZY, I1. If we want V2, it will just be ZY, I2. If I call this 0, sequence impedance, then this will be Z0, I0, this will be Z1, I1, this will be Z2, I2. So from these expressions, realize that they have no relationship with each other. So in symmetrical form, we say that the symmetrical components circuits are decoupled. Say decoupled because all three components are independent of each other. Okay. However, when there's an unsymmetrical fault, then there's a certain connection between the components. Okay. So we have our zero sequence. I have a zero sequence network. Let me draw it now. Okay, let me draw it this way. These are 3ZF. Okay, let me do it box. Let's say this is Z0. So this will be our impedance to ground, and this will be any zero sequence impedance they give. It's have something like this. This I0, and this here will be the zero sequence voltage. Okay, so in the same way, for positive sequence, this will be positive sequence voltage. Sorry, impedance. You know that for all the components, they don't have a voltage source except the positive sequence. So the positive sequence has a voltage source here. Let me call it E, and the current I1. We call this the sequence voltage. Then for negative sequence Z2, we have V2. So when there's a single line to ground fault, then you connect all the components in series. In series, we are here series. So Z1, you put Z1 here. You put your E here like this. Then connect this to this in series. The same way you can put your Z2 here. The diagram like this. Then you connect this and this in series. And finally you connect from here to here. You have your diagram for solving single line to ground faults. Very.
So we are back. Thank you for waiting for us.
Alright. Please sorry for the delay. The network is not really good here. Okay. So what I was about to say before I was disconnected, I see that the 3ZF that I have here, usually they put it here. So you normally see the diagram as normally see it as where your 3ZF is here. This is Z0, Z1, Z2, and this is VF. Okay, alright. So yeah, this is what you have for single line to ground fault. Okay, so alright, so let's take a very quick example. Let's just formulate an example and solve it. Let's formulate an example and solve it. So let's assume that our positive phase and impedance is, let's say, okay, let's take, to make things simpler for us, let's take them all as let's say reactance values, because in the slides we have reactance values. So let's take x1 to be, let's say J 0.4, say x2 to be J0.3, and let's say x0 to be J0.2. Let's take our ZF to be 0.1. 0.1. Okay. Take our VF. Usually, that's our terminal voltage, by the way. Let's take it to be, let's say 1 angle 0. Please, before we continue, let me mention this. Before you do everything, whenever you are doing force analysis, you should convert all your values to per unit. Please don't forget, change all your values to per unit so that all your answers, after getting all your answers, you can then find, let's say, base current or base voltage, multiply by the per unit to get the actual current, actual voltage, so that there won't be any mistakes. So I'm taking all the impedances as in per units, and this voltage, so I'm taking it as it's in per units. So from here, we can input this here, J0.2, J0.4, and this is J0.3. Now 3 ZF will be 3 times 0.1, which is 0.3. From here, if we want any current, you know that if we had drawn them separately, this would have been an I0, this would have been an I1, this would have been an I2. Let me put the I2 here, right? But then since they are all in series, there's only one current flow. Let me call it I. And we know that since these are symmetrical component currents, we should know that when we get our I0, or let's say our I0, and then we want the fault current of IA, it should just be 3I0. So all you have to do from here is to do VF over Z0 plus Z1 plus Z2 plus 3ZF. Do this and you get your I0. Multiply by 3. That means if I want my fault current, straight away I'll do 3VF all over Z0 plus Z1 plus Z2 plus 3ZF. Yes. And then if in the question they give any S, let's say 200 MVA, and you know the voltage in the phase, because there's a phase to ground fault. You know the voltage in the phase, let's say 240 volts. This is the phase voltage. Then you can find your, or let me take this as line voltage. So let me make it 240. Leave as line voltage, B line. So I can find my current as S over root 3 BL, and that will give me my IL or my I base. I use my I base to multiply my IA per unit. I'll get IA actual. And with that, you are done with single line to ground fault. If you don't understand anything, please send to the comment section so that we'll be able to address your issues. Okay, we are moving on to line quickly. We're sorry for the delay. We've been having trouble with our network. So for line to line, you can have, I'm ignoring the impedance part. So we have this. So this is A, B, C. Let's assume we have a fault between line A and line B. Like I said, we always put an impedance generally to represent fault. So you know that the current will be flowing this way and flowing from line C. So let me call this IB, call this IC. Since there's no fault current here, IA will be 0. And from here, this is just line to line. So there's no ground impedance, right? This ZF is not going to ground. Okay. So from here we can say that IC is equal to negative IB. And from here, can tell that IB is equal to negative IC or IC equal to negative IB. Very, very simple. So if we want our symmetrical components from here, it's equal to 1/3 of 1, 1, 1, 1 h squared, 1 h squared h of IA, which we know as 0, IB, and IC, which we know as negative IB. So if I clean and replace with what we actually know, the right ones, we have 0 IB, negative IB. This is what we have. Okay, so if I write my expression for I0, I'll get 1/3 of 0 plus IB minus IB, which equals 0. If I write the expression for I1, I have 1/3 of 0 plus HIB minus H squared IB. Which is equal to 1/3 IB into H minus H squared. This is my expression for I1. For I2, I'll have 1/3 of 0 plus H squared IB minus HIB, which can be simplified as 1/3 IB into H squared minus H. We have our expressions for I0, I1, and I2. From here, we can see that if we look at I1 and I2, the expression very carefully, you see that I2 is equal to negative I1, or I2 plus I1 equals 0. Very simple deduction you can get from here. Okay, so from here, if I take, there's a force at B, there's a force at C. If I want, let's say, the drop across here, it will be VBG. Since I'm taking IC as negative IB, so I can also say that VBG minus VCG will give us IBZF. So the voltage minus the voltage will give us IB times ZF. So we also have this expression. Now if I want to express VBG using symmetrical components, I know it to be V0 plus V1 plus V2. And let me make one reference so that we all know what I'm talking about. You know that V0 is VA plus VB. Wait, sorry. Before I make a mistake. VA is VA0 plus VA1 plus VA2. VB, if I'm making reference to phase, say A, then to be VA0 plus H squared VA1 plus H VA2. VC will be VA0 plus H VA1 plus H squared VA2. Okay, so let's make reference to A, since let's make reference to phase A. So here VBG will be given us VA0 plus V H squared VA1 plus HVA2 minus VCG will be given us VA0 plus h VA1 plus h squared VA2. Sorry. Okay, so you know that VA0 will cancel VA0. Now we have h squared minus h VA1. I can use minus, okay, it would have been plus h squared VA2, which is the same as h squared minus h VA1 plus, sorry, minus h squared minus h VA2. Okay, so this should be equal to our IB. So what would be the expression for IB? We know that if I wrote this, let's hold on. Right. Let me take some things off. It's too much. Alright, now IB. So I'm making reference to phase A. So I'll get IB can also be expressed as IA0 plus h squared IA1 plus HIA2. I hope we are all aware that this is what we have. I mean, from the voltage expression I wrote. But we know that the IA is 0. So when we wrote the symmetrical components, we realize that I0 gave us 0. Oh, I don't even know when I did it. From here, when we wrote the expressions, yeah, we realize that I0 gave us 0 from here. I1 gave us something, I2 gave us something, but I0 gave us 0. So that means that our IB is equal to h squared IA1. But the relationship between I1 and I2 is that I2 is the negative of I1. That means I can write this as minus HIA1. That means IB can also be given as h squared minus HIA1. If I put everything together, I'll have h squared minus h VA1 minus h squared minus h VA2 equals h squared minus h IA1. So h squared minus h, I divide it by h squared minus h. I'll get VA1 minus VA2 because, so I didn't bring my ZF. So my ZF should be equal to IA1 ZF. So you can get this. So you can see that the relationship for getting your fault current has nothing to do with the zero sequence impedance. That means that when you are doing line to line, you have nothing to do with zero sequence. So we take the zero sequence. So we say that the zero sequence circuit is decoupled, but then the positive sequence and the negative sequence are coupled. So this is what you have. You have this positive sequence. Positive sequence has a voltage, and they are coupled. But from the expression we had, we realized that I2 equals negative I1. So I'm going to connect so that I2, which let me put I2 here, or let me put this our negative sequence and this our positive sequence. So I'm going to connect this such that I2 equals negative I1. That means that I'm going to connect these two together. I'll put my general ZF here such that I1 is going this way, I2 is going this way. Connect this, and we know that this voltage here is our V1 and this voltage here is our V2. So from this diagram, you can see that V1 minus V2 is equal to I1 ZF. Yes, simply, and then you get your current. Okay, so your fault current is, so you can either find, you want IB, and we got I1 as 1/3 of, let's say, H squared minus H, I don't recall, but we got an expression like this. And if we get our I1 from here, then we can find our IB simply by doing 3 over H squared minus H I1, then we'll get our IB, which I don't know what you get from this. Yes, so from here you can get your fault current easily. And then if they ask you to find the fault voltages, which I didn't mention when I was talking about the single line to ground, you should know that since the positive sequence has already has a voltage before, already has a voltage there before, let's say, the positive phase voltage. That means that if I want the overall V0, V1, V2, because they don't have any voltage in their circuits, but positive phase has a voltage in its circuit, minus, I'll do Z0, Z1, Z2, multiplied by I0, I1, I2. So when I do this, I can easily get my expressions for V0, V1, and V2. So you realize that V0 is equal to negative I0, Z0, which, so these are expressions I've already written for you already. I've already written for you. Vf minus I1 Z1. V2 equals I2 Z2. Very simple. So you get this, and then if you want the phase voltages, you can easily multiply by 1, 1, 1, 1 H squared H, 1 H squared. V0, V1, V2. So in case they ask you for phase voltages, you just get your expressions for the voltages and then you find VA. Alright, I realize that in the single line to ground, I1 was 0, I2 was 0. That means V1 and V2 will also go to 0. So you can, if the fault occurs in phase A, you get the fault voltage will also be an A voltage. If the fault occurs in phase B, the fault voltage will also be in phase B. If the fault occurs in phase C, the fault voltage will also be in phase C. For line to line, we got only I0 to be 0. That means we'll get current I1 and we'll get I2. So that means you'll get V1 and V2. So for line to line, it's only VA, assuming the fault occurs between lines B and C. Only VA will give you 0. VB should give you an answer. VC should also give you a number. Yes, that's for line to line. Please don't confuse it. Okay. So and then finally we'll do double line to ground fault. Double line to ground fault. Okay, so I draw my 3 parallel lines again. So one line, so I'll use IB and IC again. So we have IB, sorry, we have IC, and then it's to ground. So we always put if there's a ground, then the fault impedance we put it at where ground is. And here is IB, here is IC. This phase A, phase B, phase C. So from here, you can see that the current coming here will be IB plus IC. Notice as ZF. So from here, if we want VBG to be equal to, we want voltage from phase B to ground. So giving us IB plus IC ZF. Same way if we want VCG, should also give you, please hold on. Okay, so we move on. So if we want voltage from C to ground, it will also be IB plus IC ZF. Then from here, you can easily say VBG equals VCG. That's that the voltage that will be expressed in the line B, from line B to ground, will be the same voltage in C. Alright, if we try to write expressions for this, in reference to A, it will be VA0 plus H squared VA1 plus H VA2 should be equal to VA0 plus H VA1 plus H squared VA2. VA0 cancels VA0. I have H squared minus H VA1 should be equal to A squared minus H VA2. This cancels this. VA1 equals VA2. Can easily see that our symmetrical voltages for positive and then the negative, they are the same. So I can say V1 equals V2 or V1 minus V2 equals 0. However you say it. Okay. So this is what we have. Okay, the same way, so we have this already. The same way, if I write the expression for this, I can write this. So let's write for IB plus IC. Now IB will be given as IA0 plus. Let me take the phase out. So I just write I0 plus H squared I1 plus H I2 plus IC will be given as I0 plus H I1 plus H squared I2. This is IB plus IC. Multiplying ZF, it should give you VBG. VBG, which is V0 plus H squared V1 plus HV2. Okay, if I simplify this, I'll get 2I0 plus H squared plus HI1 plus H squared plus HI2, all multiplying ZF. And we know that from the expression we had, we got V1 to be equal to so we got V1 to be equal to V2. So we can write V0 plus H squared plus H V1. Okay, so this gives us 2I0 plus, please you should know that H squared plus H will give you, I think, -1. Right. So this will give us 2I0 minus I1 minus I2 all times ZF. This should give you V0 minus V1. Yes. Okay, so we've gotten this expression. And then from here, we know that I0 plus I1 plus I2 should give us 0. So, which means that I0 is equal to negative I1 minus I2. So when we substitute negative I1 minus I2 as I0 here, then this expression becomes 3I0 equals V0 minus V1. Okay, and this gives us our expression that we need. Okay, so we have these expressions. Oh, please, I left our ZF out. So there is 3ZF I0 to give us V0 minus V1. Okay.
Message and easier to pass.
Please, you should know this expression already because from your symmetrical component, you know that I0 plus I1 plus I2 is 0. When you substitute, you get this. That means that from here, so you can see that I1 plus I2 equals negative I0. Or you should know if for, so for a single line to ground, you have only one component, IA. If the force is at IA, you have only IA, you have only I0 that is working in the circuit. For line to line, you have only, if it happens between phase B and C, you have only, present this as a diagram. Realize that for single line to ground, we just put everything in series because we have only one current flowing, so we just put everything in series. For double line to ground, we parallel positive and negative sequence circuits. That's why for line to line we had this, if you remember, I2 here, I1 here. This was where this was V2 and this was, sorry for the diagonal I've given you, but yeah, this is what we got. This is a diagram we got for single, sorry, line to line. But now for double line to ground, like that all currents are at work or all circuits are coupled. So we have I1. Since I1 is positive phase sequence, our VF is here. No, I1 plus I2 then I0, they are all supposed to be, the sum should give you 0. That means they are meeting at a common point. So if this is a common point, I can put my Z2 here, this is Z1. I can put my Z2 here, like that. And then I2 will be going this way. And then I come and put R3ZF. And let's say any Z0 that they gave in the question. And I give this direction. I combine the circuits. Yes, and this will be the diagram for double line to ground faults. Very, very simple. Okay, yeah, so that's what you have. So let's see if we can do some numerical examples so that we can move on fast from here. Okay, so let's go to the slides. Since I can't project the slides here, so I'll just write the things we need for the question. So example 10 from the slides. A three-phase star-connected alternator with its neutral point solidly edged is excited in such a way as to give 3.3 kilovolts on open circuit. We have positive, negative, and zero sequence impedances are given. Positive is J 0.6, negative is J 2. This is J 6.0, this is J 2.0, and then zero sequence is given as J 1.2. So a resistive fault occurs between a single line and earth and the alternator terminals on phase A. So that means we are doing single line to ground faults, and the fault occurs on phase A or line A. And they give a fault resistance as 0.5. The resistance I was talking about that they don't usually give. If they don't give, take it as 0. 0 impedance means short circuit. It doesn't mean open circuit. Please don't confuse the two. So we have a resistive fault occurs between a single line and earth at the alternator terminals on phase A. The resistance RF of the fault is 0.5 ohms. So I put my unit here, ohms. Okay, calculate the fault current. Okay, so we have to find fault current, which is very, very simple. All you have to do is find our symmetrical components, which I believe everyone knows how to do. So we find our symmetrical components. They give us a voltage. Where is it? A three-phase star-connected alternator with this neutral point solidly edged. It's excited in such a way as to give 3.3 kilovolts. So they're giving us the voltage that you use for the positive phase or terminal voltage. So this is your terminal voltage. Let's call it, since that voltage is only given to positive phase, this EA1, positive phase voltage. The 3.3 kilovolts is supposed to be voltage for positive phase impedance. Now this is a single line to ground fault. There's a single line to ground fault. So from the expressions we've obtained, we know that for a single line to ground fault, we only need to find one current, and then we multiply that current by 3. We get the fault current. Very, very simple. So instead of finding one current and multiply by 3, I'll write the overall expression as 3 times the voltage. This is very, very simple question here. And since the voltage is a line voltage, we can change to phase by dividing by with 3. These are things we already know. And then we divide by Z0 plus Z1 plus Z2 plus 3ZF. Please do this and then you get your fault current IA. Very, very simple. So the first question defines fault current. So you can just find fault current from here. So this will be MC 9900/3 all over. So you put your impedances there. We have J6. So these are all reactances. So you combine them, we have 9.2 plus. There's a resistance, but we need 3 times that value. So that will be 3 times 0.5. Use your calculator. The calculator will give you 3 times angle negative 80.74 degrees, which is 6132. Hey, 613.2 amperes magnitude. The angle is there, right? So this is the force current magnitude. I wrote it this way so that we'll get that current that is flowing. Okay, we know that, from the stream down today, we should know that when we have single line to ground fault, there's only one symmetrical component current that is flowing. Or we know IA0 should be equal to IA1 should be equal to IA2, since we put everything in series. So this is the IA, either IA1 or IA2 or IA0, whichever you take it as. It's supposed to be 204.4 angle negative 80.74. We need this to solve our second question, which is to find the voltage of phase B to Earth at the fault current. So they want you to find voltage. They want you to find phase voltage, but what you have is a symmetrical component current. So you multiply the symmetrical component current with its impedance. So if you want phase B, all you have to do is multiply. Okay, we need IB. Everything will be simple. We just need to find BA0, BA1, BA2. Or let me say V0, V1, V2. Let me just take the phase out. This will be equal to, like I told you, the terminal voltage is only on the positive phase. So we'll put the VF here, this 0. 3 minus, okay, 0, 0, 0, 0, 0. Z2 is J0, sorry, 2.0. This should be J6.0. This is J1.2. Multiplied by our currents. All the currents are the same. All the currents are equal. So if one V0 is just negative I0 Z0. If one V1, V1 will be, so I call this EA1. So let me write EA1 here. So V1 will just be EA1 minus I1 Z1. V2 will just be negative I2 Z2. When you get these components and you want phase B voltage, then you just write your symmetrical components for phase B. This unsymmetrical voltage, just if you know symmetrical component very, very well, this topic is actually very, very simple. So if you want VB, VB is just VA0 plus H squared VA1 plus H VA2. And we will get VA0 as I0 Z0. So You get all these values, just put them inside. You get your phase voltage VB as 994.86, angle negative 120.28 degrees. Yeah, so that's what you get. Please, if you are confused why we got these formulas, you should just go back to our block diagram for. So this is Z0 and this is V0, Z1, EA1, this is V1, Z2, this is V2, and this here is our 3RF. So if you want V0, V0 is I0 Z0. But if you want the overall, it is 0 minus I0 Z0. That's why you get negative I0 Z0. So you get your expression from here, and yeah, that's it. Okay, so that's it for single line to ground. Let's take the next example. The second example. I don't even know. Okay, so you have this question: 100 kilometers, 400 kilovolts, 100 kilometers, 400 kilovolts transmission line is subjected to an A phase to earth fault at 80 kilometers. That means that this is also a line to ground fault. Oh, okay. So the line is 100 kilometers, and the fault occurs at the 80th kilometer. The fault resistance. So we have going to ground from here. Well, the fault occurs at the 80 kilometer points. So that's where the fault is. So we have our fault resistance giving us 10 ohms. Okay. Calculate a fault current. They give zero sequence impedance as 0.5 plus J8. They give positive sequence impedance is equal to negative sequence impedance 1 plus J6, and then the gain impedance. Okay, the line impedance is 2. So the impedance of the line they give it as components. So for ZL0 it is 10 plus J88. For ZL1 because ZL2 equals 1.8 plus J31 ohms, ohms. Okay, so this is what we have. Okay, so you are supposed to calculate the fault current. Like I always say, every single line to ground fault, the fault is just IA. It occurs at phase A, so you can just write IA is 3EA1 over Z0 plus Z1 plus Z2 plus 3ZF. Now you know that. Okay, this is general formula. Don't say my Z0 here is not the Z0 here. I'm just writing a general formula for you. Okay, now if I want zero sequence impedance, you can see that there's a zero sequence impedance here, there's another zero sequence impedance, right? So all you have to do is to add the sequence impedances. That will give you your overall. So then write 00, 11, 22. So that it won't confuse anyone. Here I want Z00. I'll just do Z0 plus ZL0. However, the impedance, the line impedance they are giving you is for the whole 100-kilometer line. That means that if you want the impedance at the 80-kilometer, you just have to do 80 over 100. It's like a percentage. 80% of the impedance. So all the line impedances you see, you have to use 0.8 times the line impedance when you are solving. That means your Z00 is to be Z0 plus 0.8 ZL0. Your Z11 will be Z1 plus 0.8 ZL1. Z22 will be Z2 plus 0.8 ZL2. Yes. And then your false impedance was given, so very simple. You can just find your current from there. Please don't forget, the voltage they give you is a line voltage divided by √3. Don't let that beat you. Okay. And from there you can get your answer for the question. Alright, please let's see, the last question. Or please, you can solve the other examples in the slides. You can go to the slides and then let's move on to chapter 3. Let's continue from where our good brother Tamakloe ended the last time. No mind, no. Okay. So we are moving on to chapter 3. We are done with unsymmetrical form. If you don't understand anything, please let us know. Bring to our attention. Because this stream won't be done again anyway. Okay. So our good brother Tamakloe actually did a lot with us. He took us through almost half of Unit 3. That's a very good work done. We should thank him very well. You can thank him in gifts by using gifts or in kind too. Please vote for him. Very important. Please vote vote for our brother Tamakloe for most versatile student, please, and academic excellence. Please, he has to come from our department. He has to come from, and he's also our course mate. Please, we need it. So please vote for him. For academic excellence, he is third. Please, that doesn't speak well of us. It doesn't speak well of us at all. Please, let's vote for him so that he can top the academic excellence board. And then, most versatile is already winning. That doesn't mean you should stop voting. Please, we need to give them the gap so you know that electrical theory is not small. Thank you very much. Please, let's move on. Okay, so he ended us with the assignment 1 in the slides. So we are moving on to generator load model. Generator load model. Okay. So at the generator load model, all we want to know is from the beginning of Unit 3 actually, I'm sure he mentioned that P generation equals P demand plus d Ke dt. That means that, so ideally we want power generated to be equal to power demanded. We want the exact amount of power you need. That's the power we want to generate. However, that's not the case. So we have situations where power generated is greater than power demanded, or the device is on and suddenly you turn something off. That means demand will go down. At that point, generation is higher than demand, so it will cause the rotating part of the system to move faster, which means that speed will increase, frequency will also increase. However, when we switch on loads, of an already existing system, what will happen is that the demand will exceed generation, and then the rotating parts will actually slow down to compensate for the power that is needed. Okay, that's all we have. So we are going to write an expression. Now we know that there's a KE dt, but we don't know what this KE stands for. Our kinetic energy. This kinetic energy is giving us HPR, and our H is defined as an inertial constant, or the stored kinetic energy. Defined as the stored kinetic energy at synchronous speed. Please look at this. In the slides, you see synchronous speed as ohm naught. Ohm naught. Please, this ohm naught here is representing mechanical speed, or let me say it's all speed, but this is mechanical part. So omega is actually an electrical component. So if you want to change synchronous speed to electrical, if you want to change from mechanical to electrical, you multiply by pole or pole pair, however you take it. So you will see an expression where this is changing to this somewhere. So I'm just telling you right now so that when you get there you will know. So this is actually a mechanical component. Multiply by P, you get electrical component. Yeah, that's where it came from. Okay. So is that at a frequency F0, this is our our kinetic energy. So we are taking F0 as our normal frequency. Our normal frequency is a kinetic energy that is already there. HPR. So from here, that means if we do any d WKE dt, okay, it's the same as DHPR dt. Right? We have not seen any expression here that we can differentiate, so it's looking weird. But let's move on and we'll see where the differentiation comes from. Okay, now this is our kinetic energy at normal frequency. But what if the frequency increases to, let's say, a change in F? Let's say it increases slightly. Then our new kinetic energy is giving us our old kinetic energy times this expression here squared. Now, because this change in F here is a very small change, so when we expand, we will get F0 squared plus 2F0 change in F plus change in F squared all over F0 squared. Okay, since change in F is very, very small, when you square it, you get way smaller value. So let's take it as 0. That our new kinetic energy will given us old kinetic energy times F0 squared plus 2F0 change in F all over F0 squared, which can be expressed at this kinetic energy. It has this formula here. So we can write HPR multiplying, if I simplify that, I'll get 1 plus 2 change in F over F naught. Very, very simple. So we know that our new kinetic energy WKE is approximately, it's an approximation because we are saying this change in F is 0. Well, it won't be 0 exactly, but that's why it's an approximation. HPR multiplying 1 plus 2 delta F over F0. Okay. So from here we do our rate of change of kinetic energy with respect to time. We're giving us HPR this goes to 0. 1 goes to 0 when you differentiate the first time. Then you have, so let me bring, so you have 2 over F naught D, change in F dt. This gives us 2 HPR over F naught. This is my F naught. Sometimes I write the 0 as an exponent. Sometimes I write it here. Please, it's the same thing I write. The change in F dt. These are rate of change of kinetic energy with time. Okay, so this is what we have. Like I said, the H is defined as our stored kinetic energy at synchronous speed. This synchronous speed representing mechanical and omega naught representing electrical. Very simple. Okay. So this kinetic energy here, this kinetic energy expression we've gotten is for rate of increase of stored kinetic energy in a rotating mass of generator. So we've gotten it for in a rotating mass of generator. What of the load? So that one can be expressed as del PD del F, change in F. And we are calling del PD del F as B change in F. So we have these expressions. We can put them together. Change in P generated minus change in P demanded. So given us 2 HPR over F naught D delta F dt plus B delta F. Now this is power. B is also a rate of change of power. It's a rate of change of power. So if we divide through by our PR here, then we'll get everything in per units. So you will see that expression in the slides somewhere. Okay. So let's skip the reading part. You should know the meaning of dead band of governor. We talk about dead band of governor. We're talking about, you know that when demand increases, the rotating parts slow down. Your governor is supposed to respond to that change and then increase frequency. However, it doesn't increase frequency immediately, or it doesn't sense the change immediately. The time that it will take, or the time that the governor doesn't take action, or the time it will take before the governor takes action, that's what we call the dead band of governor. And okay, then we're going to talk about governor time lag. We are just talking about, you see, after dead band, governor will respond. When the governor responds, the power doesn't change immediately. So when the governor responds to a change in, say, frequency, the time it will take before the power will also change and then normalize. That's what we call the governor time lag. So for governor time lag, the governor is already in action. It is working to change the power. However, the time it will take from sensing the frequency to the time the power will change, that's what we call the governor time lag. Okay. So if we're able to understand these terms, then we can move on. Okay. So you see example 1 here. Let's do one example and then we go. We have a 100 MVA synchronous generator. S is 100 MVA synchronous generator on full load at frequency 50 Hz. The load is suddenly reduced by, that means our change in load. Since it has been reduced, it's a negative change. Please, I hope you know that. Since it has been reduced, that means the new power is smaller than the original power. That means it is negative 50 megawatts. Due to time lag in governor system, the main supply valve begins to close after 0.4 seconds. So our time lag is 0.4 seconds. So what they are trying to say is that when the governor acts, it will take 0.4 seconds before, since there has been a decrease in load, it will act to reduce power. So it will take 0.4 seconds before the valve will close, so that it will reduce the power to the load, the demanded power. Yeah, that's what they are saying. Okay. So determine the change in frequency that occurs in this time if change in load due to change in frequency is negligible. Change in load due to change in frequency. What they are talking about is change in load due to change in frequency. That's our B. They are saying 0. They're giving us H as 5 megawatts, or let's say megajoules per MVA. Determine the change in frequency. Okay, so we just write change in PJ minus change in load, giving us 2H PR over F0 change in F plus B change in F. Now, from all the explanation we've written, they didn't tell us that the synchronous generator, there was a change in the power that the generator is generating, the 100 MVA. There was no change, which means our change in PJ is 0. Okay. Our B is also 0, so this goes to 0. So this is dt. Now we want the time the change in frequency that occurs in this time. So we want change in F. This is 0. So if I make change in F the subject, I can do D. This is the T equals negative delta PD F0 all over 2HPR. So D equals negative change PD F0 over 2HPR dt. Integrate. They only gave one time. Okay, so this becomes a change in F as negative change in PD F0 T over 2HPR. The negative times negative 50 megawatts. Our frequency is 50 times 0.4 seconds. 2 times our H is also 5 megajoules per MVA. Our PR, which you know as hundred MVA. Okay. So negative cancels negative. Oh, we have to solve this. This goes here 10. This goes here 10. This goes here 5. This goes here 0.2. That means this will give us 2.5. Change in F. So our delta F is 2.5. Okay. Sorry. Our delta F. Hey, 0.2 times 5 is 1. Please, I'm sorry. Our delta F is 1 hertz. So it's a positive frequency. That means our new frequency F plus F0 plus change in F will be 50 plus 1, which is 51 hertz. Okay. So we've gotten our change in frequency now. We've gotten the actual frequency, 51 hertz. So that's it for this question. So next question. Next question is a control area has no intertires. The load demand increases from 5,000 megawatts to 5,200 megawatts. So the change in demand is 200 megawatts. This is a positive change. The kinetic energy of the rotating mass before the increase in load. Kinetic energy before the increase in load, that is WKE0, which is the same as HPR. They are saying it is 25 1000 megawatt second or megajoule. The resonant frequency F is 60 hertz, and here they gave us B as 83.3. Similarly, they didn't tell us that the generator changed or the generation by the generator changed, so our change in PG is 0. So we have negative change in PD because 2 HPR over F naught D delta F T plus B delta F. Now let's see. They determine the frequency variation with time. They want frequency variation with time. So all we have to find is okay, we are back. Hey, data keeps finishing. Alright, so here they want us to find let's find frequency variation with time. Okay, so we want frequency variation with time. We have delta F here, we have delta F here. So let's see. We have negative 200 equals 2 times 25,000 all over F naught was given as 60 d delta F dt. B is 83.3 delta F. When we simplify this, we get negative 200 equals 833.33 d delta F dt plus 83.3 delta F. Now you have d delta F dt plus 0.1 delta F equals negative 0.24 divided by 833.33. So we've met we've met a very good friend. We used to have second year differential equations. We solved this. The only one I remember is using the find our I integrating factor method. That's the one I remember. So that's what we are going to be using. Our I is giving us e to the power integral of I should put it on.
How is pain?
So you solve this and then you kind of get our change in F as so our I here will be e to the power 0.1 t. So you just have to use this value here to multiply to. So you have e to the power 0.1 t the delta F dt plus e to the power 0.1 t 0.1 change in F equals a 0.24 e to the power 0.1 t. Okay, then we can put this together as d e to the power 0.1 t d delta F dt. All dt is equal to negative 0.24 to the power 0.1t. Then bring the t here, integrate. We have e to the power 0.1t delta f dt. Sorry. So we are integrating over 0.1 is the power 0.1. So you have this. So changing f plus a c. Changing f will be equal to negative 2.4 power 0.1 t plus c is the power negative 0.1 t. Changing f equal to 0 at when it's working normally, we don't have any change in frequency, so we have this. When you solve, you get our c as 2.4. Substitute, and then you get a final expression delta f as 2.4. Okay. Change f will be negative 2.4 into 1 minus e to the power negative 0.1 t. So this is what we have as our expression for our delta f. Okay. Now the next question is to find the drop in the frequency if time delay in the operation of governor is 4.3 seconds. So now they want the drop if time delay is 4.3. So what you have to do is change f equals negative 2.4, 1 minus e to the power negative 0.1 times 4.3. And by simplifying the delta f, you get this as negative 0.84 hertz. And our original frequency, so that means our new frequency will be 60 minus 0.84 is 59.16 hertz. Yes. And now we are done with the question. Okay. Let's just mention the last thing that we did in Unit 3, and then we'll call it 9. Okay. Alright. So power flow to a transmission line. So this power flow, they use ABCD parameters. So for ABCD parameters, our Vs is given as AVR plus B plus BIR, and our IS is also given as CVR plus DIR. So from here, we want our expression for VR. Very simple. Vs minus BIR all over A. Hey. We want I, let's say R, to be IS minus CVR all over D. Yeah. Or you can also say our VR is equal to Vs over A at IR equal to 0. And you can get all your expressions by, if you remember the parameters, hybrid parameters or ABCD parameters or any parameters you remember, you can use them to solve it. Okay, so we get our IR expression as Vs minus AVR all over B from the first expression from equation 1. So So it is the same as Vs over B minus AVR over B. Okay. Now you should know that S power or apparent power is always VR IR conjugate. This one will give you a PR plus a positive QR. So we have our IR here. If we do a conjugate of this and we multiply our VR, so first let's take our VS as an angle. This is our transmission line system. This is our generator, which is connected to an infinite bus. So the infinite bus, we take it as the reference angle 0. This is our generator angle delta. So the power here is what is PR plus JQ. Power that gets here. Okay, so this is the diagram we have. And our VS is at an angle delta. Our VR is at an angle 0. A take it as A angle alpha. B take it as B angle beta. D take it as D angle delta. So our SR is supposed to be VR IR conjugate equal to, so just add IR to this formula to get V. Get VS VR over B and then you get minus AVR squared over B. So since the IR is conjugate, that means that the voltage in the current formula goes negative. That means the B, so here is supposed to be delta minus beta. However, because so please let's finish hard. So since the IR is conjugate, since you are doing IR conjugate, all the angles reverse. So you get VS VR over B angle beta minus delta minus AVR squared over B. This was supposed to be alpha minus beta. Because the IR conjugate becomes beta minus alpha. Angle beta minus alpha. Yes. So this is all you need for the ABCD parameters. Now if this is S, so if you want PR, you just take the real part of this. That means that you just need to take the cos of the angles. So if you want real power, which is P, so PR will just be VS VR over B cos of beta minus delta minus AVR squared over B cos of beta minus alpha. If you want, if you want the Q component to, we just use sine, and with that you can. That's all you need for the power free transition line design. You can use this understanding to solve all the questions. Okay, so thank you very much for staying tuned with us throughout the stream. Thank you for your presence here. So we are ending the stream for today. Tomorrow in the afternoon around 3 p.m. we'll be doing the, so yeah, we'll be doing a stream for control systems. But for unit 4 of the power system analysis, we'll do it after controls on Monday or Tuesday morning. So we'll see you then. Have a great evening.